Okay, so here we're talking about the photon model. So we're going to get a little bit more into depth about light and talk about these things here. So here, this kind of goes to what I was talking about earlier. This is our, Bohr model, which again we know is wrong, but we're going to take that with a grain of salt. And here you can see like the different energy levels that like electrons would be at, and how, if they fall down from like a higher energy level to a lower energy level, they are going to give off a certain amount of energy with that, and that energy will be associated with a very specific frequency of light. Okay? And so here, this is showing that like if it falls from like the 5th energy level to the 2nd here, that'll give off a violet photon, which you can see an example of the atomic spectra here in the notes. Now, I do have some spectroscopes, and you may have used those in chemistry, where you can look at elements through the spectroscope, and you can see these spectral lines. If not, I do have some here, and I think we can get them out. I mean, we'll probably get them out next week. Theoretically, everybody's here, right? So again, Bohr model wrong. Here's some of the main reasons that are wrong with it. It fails to provide any understanding of why certain spectral lines are brighter than others. If certain spectral lines are brighter, what that means is that the electrons are falling down, emitting those photons more frequently than others. And so the question is, why do electrons prefer this particular frequency than, say, frequency B or C? Okay. So that's one of the biggest things. Like it addressed the fact that, like, yes, we have these fundamental energy levels, but it doesn't show us why certain lines are preferred over others. And there's no mechanism for the calculation of the transition probability. That's essentially that's the same thing there. Here, number 2, it says the Bohr model treats the electron as if it were a miniature planet with definite radius and momentum. That's not true. It's in direct violation of the uncertainty principle. So the uncertainty principle, we'll talk about that in this unit. I don't know if we get to it in this set of notes. The uncertainty principle says that basically you can only know so much about an object's position you can only know so much about an object's position and its momentum. You can think about momentum, but think more about velocity. But essentially, the more specifically you know of one, the less specifically you know of the other. To know both of them actually to know both of them very specifically violates the uncertainty principle, which is one of the fundamental laws physics is built on. Why that is, we'll kind of get into that when we get to the uncertainty principle specifically. So basically, it says that they can't be simultaneously determined. Basically, the more you know about one, the less you can know about the other. And then number 3, the Bohr model gives us a basic conceptual model of electron orbits and energies, but the precise details of spectra and charge distribution must be left to quantum mechanical calculations, as with the Schrodinger equation. So one of the big things about quantum mechanics that I certainly never got for the longest time is I thought like quantum was some weird, mysterious word that just meant it was hard. Quantum or quanta just means it has very specific things. So like we're talking about the Bohr model has very specific energy levels. Those are quanta. Because what quantum mechanics is talking about is that everything seems to be quantized. That it has very specific settings. Like you think about like on your radio or your TV where you turn up the volume, like it goes like 1, 2, 3, 4. Like those are very specific settings. Like there doesn't seem like when you're turning up the volume on your radio, there's no like 1.5. Like it's very specific. Why is it specific? We don't know, but it seems to be very specific, which is what quantum mechanics is all about. That everything seems to be very specific, whatever we're looking at. Very specific energies, very specific orbits, so on. So, one of the first things that comes up is waves and particles being the same thing. One experiment indicates particle-like behaviors of wave is a dim photograph. So, essentially, there was a debate raging 200 years ago, 300 years ago, 400 years ago, I don't know. There were people debating about exactly what is an electron. Is it a piece of matter? Is it a wave? And the experiment that was done was the dual slit experiment. I'm sorry, not dual slit. There's something before that. I can't remember right now. But essentially, like 200 years ago, they thought they settled it that electrons are definitely particles. And then another experiment came out and was like, no, it's definitely a wave. And they just kind of seem to be both. And I think me personally, I think it hints at the fact that we don't quite understand them. But essentially, the way things are presented is that everything can be thought of as a particle and everything can be thought of as a wave. Now, it's going to be silly to think of some things as particles and think of some things as waves. Like, for example, you basically behave like a particle. You do not act like a wave pretty much under any circumstance. If you went through and calculated your particle function, it would essentially come out to be, the size that we know to be u. If you went through and calculated your wave function size, it would essentially be, subatomic. And so basically, you can think of things act like a wave or act like a particle, depending on which one of these functions is bigger. And since your particle function is bigger, you pretty much always act like a particle. A great example of a wave, something a wave can do that a particle cannot. If you take two particles and you throw them at each other, what happens? They hit, and then what? They bounce off. If you throw two waves at each other, what happens?
They go together.
Yeah, they go together, they superimpose, and then they pass through each other. And so that's a real big indication of if it's acting like a particle or a wave. But given the circumstances, it's possible for things to act differently. Not really so much people up to our scale, but when you get a little bit smaller, when those two functions get of similar size, we get weird things that happen. And so here, for instance, it says one experiment that indicates particle-like behavior of waves is a dim photograph. So if you're taking a picture of somebody, well, that's just light, okay? And that should theoretically be just a wave, just like sound is, right? And it says if light acted like a wave, reducing its intensity should cause the image to grow dimmer, but the entire image would remain present. But essentially, they would start with a piece of film and just like let barely any light through, just like boop, and they would see what develops. And what ends up developing under very strict circumstances is not that you see the whole picture, but you just see dots that hit the page, indicating that light is acting like a particle because it's a very specific thing that hits in a very specific spot. Whereas like a wave of sound, like when I talk to you guys, the wave doesn't reach one of you guys before the other. I mean, technically it does. But what I'm saying here is not just one of you can hear me, right? Like the sound that comes out of my mouth is spread out to the whole room. People on the other end of this microphone can hear it, right? But also the people in this room can hear me because the wave spreads out in all directions. Whereas a particle doesn't spread out. Like if I throw a ball, not everyone's going to catch it. It's only one ball. And so that's what you see happening here with this photograph is that they're hitting in very specific spots. And so you're like, well, that's not a wave, that's a particle. It's just, when you take a picture, it's just a lot of them, right? A lot of particles. So then they get dimmer, and then they let a little bit more light in, a little bit more light in, and then eventually it looks like a regular photograph. So it says, in actuality, a dim photograph shows that only a few points on the detector registers the presence of light, as if the light came in pieces, not waves. Okay? So this is one of those first things that they're like, oh, okay, light is a particle, because that happens. Well, things never that simple. Here we're talking about the de Broglie and his model here. So we talked about how waves can act like a particle, but they can also act like waves. So this was first proposed by Louis de Broglie in 1924. He postulated the wave nature of electrons and suggested that all matter has wave properties. This gives us the following equations. So these are equations that we're going to use in this class. It's the first ones I've given you, I think, for this section, this unit. E equals HF So first of all, what is E?
Energy.
Energy. So the energy of a particular wave is E. What does F stand for?
Frequency.
Frequency. Does anyone know what H stands for?
Height.
Good guess. No. I'll give you a hint. Yeah, it's on that sheet. What does it say? What is H? Should be on there on your constants, if I remember correctly.
Planck's constant.
Planck's constant. Woo!
Oh, yeah.
H is Planck's constant. We're not going to get into too much depth on Planck's constant, but essentially that's what goes with the uncertainty principle as well. That if in exploring quantum mechanics, what ends up happening is it's like, okay, well, if things are very discrete, what's the smallest chunk of discrete we can have? And in this universe, it seems to all boil down to what we call the Planck's constant, that everything seems to be a multiple of the Planck length. So essentially, if you were to cut things in this universe, you could cut all the way down to the Planck length. Theoretically, at that point, whatever you were trying to cut will simply not cut anymore. Now, we've never been able to cut things down that far, but that's the theory. And so the question is, why is the Planck length the Planck length? And the best answer we have is that that just seems to be how the universe is built. That if things were built slightly differently, then the Planck length would be slightly different. In our universe, that seems to be how it is. Not a better reason for it. So H is Planck's constant. So H is the constant. So if you know the frequency of, let's say, a photon, you can tell me how much energy it has. It's multiplied by the Planck's constant. And so for things like light, the frequency of light is directly related to its color, or its wavelength. And so like violet light has a higher frequency, therefore it has more energy, and like red light has a lower frequency, therefore it has lower energy. But then we have this next set of equations here. It says lambda equals h over p, which equals h over mv. So h, we just talked about, that's Planck's constant. What is lambda? Put it upside down y. Wavelength. Still wavelength. So what is p? What's that p? It's an old p. The hint is what it turns into in the second part of the equation. What is m times v? What's m? What's v? What is it? Velocity? Mass times velocity is?
No.
Wait, I'm trying to think.
I don't remember.
It doesn't start with p.
Wait.
I don't
It
remember.
starts with m.
Momentum.
Momentum. There you go. So p is momentum, because of course p is momentum. What else would it be? So lambda is our frequency, is our wavelength, and that is equal to the Planck's constant divided by the momentum of our particle. All right? And so when you start to put all these things together, you end up looking at, like, say, a photon, which isn't supposed to have any mass. A photon can end up with momentum, which is interesting because it doesn't have any mass. So how does it have momentum? It totally does, though. It has momentum because it is energy. And energy is sort of like mass. It's just a different form. And so one of the most fundamental things about that is that literally when light hits things, it pushes on it a little bit. One of the theories of how to cause asteroids to avoid hitting our planet is to simply go up. And let's say you have an asteroid come at our planet. If we go up and paint like half of the asteroid surface, the light will, let's say it's black to begin with, we paint half of it white. Well, if it's black, it'll absorb the light coming from the sun, but the white side the light would hit and bounce off and reflect. And there would be a difference in the momentum hitting it, and so there would be a difference in the force, and you could cause it to turn.
You're looking at a moving asteroid.
Yeah, with a bomb, of course. That's actually a serious thing that NASA is looking into. Now, the problem with that is light is doesn't have a whole lot of momentum, so that would be something the asteroid have to be pretty far off for that to be really effective. But again, the problem with diverting asteroids is you can't tell you can predict where everything in the solar system is going to be, but a lot of these asteroids that come randomly, we didn't know that they were there. And so if you divert this asteroid off in a particular direction and just kind of let it go, then there's possibility of something else being over there that can divert it back. So ideally, if you're going to divert something, divert it to Jupiter. But seriously, that's why we think Earth has survived, is because Jupiter acts as sort of like a vacuum cleaner, cleaning up most of those asteroids. Like the comet Shoemaker-Levy, we actually saw that hit Jupiter back in like, what was that, 93 or something? And that's when people started going like, hey, Jupiter totally just took that hit and it doesn't look any different at all. That could have happened literally millions of times and we would never know. And it's kind of nice that it hit Jupiter because we don't live there. But yeah, it kind of looked like a series of small bombs going off on Jupiter, but if you look at Jupiter now, you would never know that happened. Unlike, if it hit the moon, you'd still be able to see that. Then we have the relationship along with the wave speed equation, which allows us to find wavelength. So C equals F lambda. C stands for what? Speed of light. And so remember with waves that y'all dealt with last year, waves says V equals F lambda. Right? V being the speed, F being the frequency, lambda being the wavelength. So this is the same equation, except since we're talking about light, we're specifically the speed is going to be the speed of light, not just some random wave speed, right? All right, fun with math. So if this is true, these equations I just gave you, then I'm just making some substitutions here.
Okay.
So you don't really need this, but this is going someplace. So E equals HF, right? That's what I gave you. Then F, it's all the C for F. You get C over lambda, right? I can substitute that in. Then I can substitute lambda in for H over P, right? So we do some substitutions there, like the H's cancel, P comes up to the top. So E equals CP. And then P is momentum, which is MV. But V for a photon of light would be C again, and that's how you get E equals MC squared. So Einstein didn't invent this stuff over here, he just like went, huh, that's interesting.
Learn from substitute.
All right, photon model. So, and I say the photon model because there's different ways to think about light, and the photon model is one of those models. We also have like the ray model, we have the wave model. This is the photon model. Which model you use just kind of depends on which and what interaction you're looking at. Electromagnetic waves consist of discrete massless units called photons. This is what we think photons are. So again, we think they don't have any mass and they're just chunks of wave, essentially. A photon travels in a vacuum at the speed of light. Right? All of these travel at the speed of light. And so the question that should be asked is why? It just seems to be a fundamental thing of our universe again. Like, why do they travel at that speed? I don't know. Why is it specifically that speed? Why not faster or slower? It kind of just seems to be one of the things about our universe. That like, basically if things are capable of traveling at the speed, this is the speed things want to travel at. And the only thing that can travel at the speed is things that don't have mass. But basically everything that's moving wants to travel at the speed, but the more mass you have, basically, the slower you end up going. Sort of. The electromagnetic wave comes in discrete chunks of energy, HF. So every single photon, if you know the frequency, we can find the energy. F is the frequency of the wave, and then H is a universal constant called Planck's constant. That's a very good video there by, what is that channel? It's a YouTube channel. English people, I can't remember. Number file. They kind of go through, I think it's number file. They kind of go through Planck's constant, and if you look at it, that's Planck's constant, which is written on y'all's equation sheet. One of the things I think is really interesting about it is they talk, about it being so small, but Again, it only appears to be small to us. You know, if our units were different, or if we were smaller, it may not seem so small. And then the third facet of the photon model is if you have enough of these photons, they look basically like one big wave. Okay? Which is what we saw with like the photo we were talking about earlier. You just have enough of them, it just acts like a big wave. And so again, this is my own personal opinion. I think the fact that we have to shift between different models either means we don't really understand something fundamental about these things we call photons, or we think, or our human brain isn't capable of thinking about what's actually going on. I think we're just wrong in our thinking here. But, you know, that's just me. But again, these chunks we call photons. Again, that goes back to quantum mechanics, that they seem to become very discrete chunks, right? Quanta. That's actually what Einstein called them, as quanta of light, like chunks of light. We call them photons later. So, here's the problem. It says we have a 550 nanometer, the 550 nanometers, so nano, we haven't seen that guy before. What prefix is nano, so that means times 10 to what? -9. If you don't know that, first of all, it says it on your equation sheet, or just memorize it. So it's a nanometer. So one of the things I'm going to do is I'm going to be lazy when I convert my units to meters. And when I say lazy, you'll see in a second. So 550 nanometers is the approximate average wavelength of visible light. So average. What is the energy of a photon with this wavelength? So average visible light, it goes all the way from red to violet. So in the middle, this is kind of a yellowish greenish color. The actual technical name for light of this frequency is called chartreuse, which is really funny because this is dead in the middle of the spectrum, so it's actually the color of light your eyes are the most sensitive to. And you guys have seen this a lot, actually. It's that sort of yellowish greenish color that you see on like road vests and stuff now, like high visibility jackets. Like, it's specifically that color because that is the color our eyes are the most sensitive to. What's funny is when they figured this out, they started painting like emergency vehicles, like fire trucks and ambulances, that color, so people could see it, because they want people to see those things. But people started looking at them going, hey, what's that? Looks like a fire truck, but it's yellow. And the problem was people weren't getting out of the way, they were staring at it. So not a whole lot of departments converted to that color. Fun fact, there is no regulation about what color fire trucks and ambulances or police cars should be. It's literally up to the discretion of whoever bought them, so typically like the city. So for example, I think like Denton's fire trucks are red, Fort Worth's fire trucks are white, Plano's fire trucks are this yellowish, greenish color. But the fire trucks at DFW Airport are this color. I feel like that's the best color, but I kind of get red because that's just what they were. But, So here, obviously, you just plug into that equation. You got Planck's constant. You've got the frequency. I don't know why I put 545. That should obviously say 550. When I'm being lazy about converting it, sorry, I know why that's different, because that's the frequency. That's not the wavelength. So I had to convert from wavelength to frequency. Is that what it works? No? Okay. Well, how do I convert from 550 nanometers to the frequency? What equation do I use? I'll write it up here. So obviously, if I want to solve this, I need the frequency. First of all, that's not the frequency. Okay. So I'm just going to use C equals F lambda. And so I'll just solve for the frequency as C over lambda. And so C being the speed of light, which is 3 times 10 to the 8th meters per second, and lambda being 550 nanometers. So when I say I'm being lazy, I know I need to convert it to meters because this is in meters per second, but I can't have nanometers here. So the lazy way, the way I usually think of it is I literally, instead of writing 550 nanometers here, I just write times 10 to the negative 9 meters. So the reason why I say that's lazy is because I literally just, instead of putting it in there, I put times 10 to the negative 9. And first of all, that's perfectly valid. Second of all, why does this look wrong? Why do I say this is the lazy way?
Not like the scientific way where it's 5 points.
Yeah, this isn't scientific notation. Because if I did that, I'd have to put the decimal here, then I'd have to change this negative 9. But here's the deal. Is this my answer? Is anyone ever going to see this? No. And if I convert it and I forget, oh, should I add that or subtract it from the already negative number? I could screw that up. And the thing is nobody's going to care if this is proper scientific notation in my scratch work. You all see what I'm saying? So like when I write it, I just substitute this in for my unit, whether it's pico or nano or even milli. I just put that in and just do my calculation because in the end, my calculation, if this was my answer, which it's not, but if this is the answer it was actually asking for, that one needs to be in proper scientific notation. Nobody cares about that. But that's why I said I'm being lazy, because some students start to freak out and be like, oh, you didn't convert it. Like, I'm not going to deal with that. It's just, it's an extra step that we just don't need to do. I've got the right units, so I'm moving on with my life. So when you do that, you should get,
Cluster
oh,
one,
I guess that's
release.
so I should get about 5.45
Cluster
times 10 to the
release.
14th, right? So you can essentially see that like 8 minus a negative 9 should get you pretty close there, right? And it should be, our units are per second, so that should be hertz, which is what you see over here. So theoretically, I calculated that right. And then you plug that in here with with Planck's constant to get your energy. Is that okay? If I skip that conversion stuff. Okay, well that's it for right now at least. We'll pick this up tomorrow.